Hey everybody, welcome to the Northwest Pinball and Arcade Show 2024. How you guys doing? Good? Yeah, sweet. Welcome to the Geek Gamer stage. My name is Chase Nunes. I'm the host for all the seminars today and tomorrow. In addition, I'm actually doing my own seminar at 7 o'clock, so a little self-plug there. Hopefully you guys can come back and play John Wick. We're going to be giving some great prizes today. But before we do that, we have a great presentation, actually a couple of them. If you have a pinball machine or an arcade machine and you're trying to figure out what does what, well, we have one of our awesome pinball medics here to give you some helpful tips to, hopefully not re-break your machine or anything like that. Ladies and gentlemen, please give it up for Mr. Victor Tan.
There will be two presentations this afternoon from me. This one is the more entry level, I guess you could call it. The second one will be a little bit more technical and you may be considered dry, but we'll wait and see what happens. So this talk is really about knowledge, acquiring the knowledge to figure out the problem for yourself. A lot of people like to use checklists, scripts, and follow through, and there's nothing wrong with that. You will get your problem solved if you follow through those checklists, more often than not. But sometimes you'll come across a problem that you can't figure out. And when that happens, you're going to need to understand how the system works in order to work through the issues to figure out where the potential problem is. And that's what this is about. Understanding the first principles, how things work, breaking down the problem into where the component subsystems are that could go wrong. So, without further ado, let's begin. This is the overview. Just so a little bit about myself. I do not have formal engineering qualifications. Everything I learned through reading and trial and error at the School of Hard Knocks. If I can learn it, then you can learn it too. You just have to want to learn it and apply yourself to it. Another caveat, a lot of my experience is Williams-based. So what you'll see me reference is Williams conventions. But that doesn't mean that the principles don't apply to Bally or Gottlieb. The principles are the same. The knowledge base may be slightly different, wire colors, connections. But a pinball machine is the same thing. It's electrical wires connected together that produce kinetic, magnetism, and output lights and display. They're all the same. They may be connected slightly differently. A thing that I like to do is think in terms of things that I'm familiar with. I have a background in medical sciences, so I like to think of a lot of things in terms of how the human body works. But there are a whole bunch of other things that you can that you can do that will help you, based on your experience, to try and relate to that. And I'll give you some further examples of that later, as you'll see. The topics that we're going to go through, terminology, and a lot of this stuff may be, well, I don't know what that is, and I don't really care to know. The most important thing is that you've heard the term. Someone's exposed you to it, so that if someone tells you about it later, you can say, hey, I remember hearing that, and then you can go read some more about it. But if you've never heard about it before, you go, what the heck is that? Knowledge, fundamental, everything you need to know before you can get started. Documentation, read it. You'll see that a little bit further. And another thing that a lot of people don't look for, or it can be hard to recognize, is patterns. When you first lift up a pinball machine, you look inside, it's just like, oh, this jumble of wires, what's going on? And I will tell you right now that there is a lot of order to that jumble of wires. It might look like a mess, but it is highly ordered. And it has to be. Because if it's not highly ordered, you cannot figure out where the problem is. And a good example of this is if you've ever lifted up an early Atari machine, every single wire is white. There's no color, there's no trace, there's nothing. It's all just white. So I guess it's ordered, but everything's white. If you open up a Williams machine or other manufacturers' machines, you'll see there's a whole different bunch of colors and a whole different bunch of trace colors. And I'll cover that in an upcoming slide. And finally, then there's approach, how you approach it, put it all together, and finally, the most important thing, and I can't stress this more than enough, is know your limits. do not go beyond them, because if you start working on boards and you trash the board and try and send it out to a repair person, oftentimes that repair person will say, well, you worked on it, I'm not interested in fixing it. So be very careful, know your limits. And please hold questions right until the end. You'll know when that comes up, the Q&A slide. Okay, so I don't need to read this aloud. You can go look it up for yourself later. But the definition of what first principles is, basically it's breaking things down, asking questions, doing some additional reading, trying to put the pieces of the puzzle together. So why do we do this? Again, it's scientific and methodical. I think I've already mentioned this. If you know how things work, then you can determine what goes wrong. And an example I use is based on my experience with the medical sciences is when you go through, you learn how things work under the normal circumstance. These are the basic fundamentals of it: histology, anatomy, and physiology. These are sciences that study how things work normally. And then, well, what happens when things go wrong? And in the human body, that is disease state. And those are other studies like pathology, surgery, and medicine. And it's the same thing in a pinball machine. It's just a different knowledge base. How do the wires connect together? What goes from here? How does that produce a result? It's exactly the same thing. If you know how it's wired normally and the thing doesn't work, solenoid doesn't fire, lamp doesn't come on, if you know how it's wired, you can figure out where it's broken. And often that is a process of divide and conquer, because there's a whole string of connections, and often the break is somewhere. Good luck finding it. But again, if you know how it's wired, you can narrow it down to find it. So again, the analogy here with anatomy, you need to know how the machine is at a mechanical level. So there's two fundamental parts to a machine. I break it down into mechanical and electrical. And the mechanical parts are things that people are often familiar with because you can see them right in front of you. Things like hardware, screws, and there's a whole different types of screws out there, as you probably, if you've had an experience with. As it's written here, machine screws, sheet metal screws, there's all different types of head types: flathead, round head, pan head, different lengths, different sizes, number 8s, number 6s, different thread counts, 32, 40. If you've been in this world of screwing screws in, you'll know. There's a whole different one that you need to pick them out. Switches. Again, a switch is just two contacts that close or open. It's a binary state. And there's all different types of switches, but ultimately the switch ends up being an on or off or an open or closed. And how it achieves that is through different means. The regular leaf switches, two contacts, a micro switch with an actuator, an optical switch with beams of light and receiving the beams of light, an eddy switch, magnetic changes in current induced by a magnet, and reed switches, switch basically opening or closing, again a magnetic based, and relays, which is basically a solenoid moving contacts. Lamps, I'm not 100% sure with Gottlieb's, but I know in Williams there are two fundamental types of lamps. A general illumination, which is always on or controlled in terms of dimming, and regular controlled lamps, lamp matrix lamps. And then, and there's three. Then there's the third type, which is flashes, which are directly individually controlled, driven, as I like to call it. And that's in this category here, the driven. The resistive loads, flashes, and inductive loads, motors, solenoids. And there's a difference between the two, and you'll need to know the difference because inductive loads require a special diode to block the back EMF, and maybe we'll get into that, maybe we won't. But again, it's part of knowing how the system is supposed to work so that when something goes wrong, diode's missing, diode's blown, you'll be able to say, that's a possible cause, I need to go look for it. And finally, as part of a machine, there's also display, but I'm not going to go into display. Okay, so I'm going to now switch to something that is fundamental And this is the other side of the machine, the electrical side. A lot of people are very familiar with mechanical. You can see it in front of you, you can move the parts, and you can see when it breaks or when it doesn't work. A lot of people have trouble with electrical because you can't see the electrons, you don't understand how things are supposed to move and flow around and what goes where. So I'm going to try and walk through this. I'm going to spend a little bit of time on this to try and help you in case you are unfamiliar with how electrical works. So if you remember all the way back into science, if you ever took science in school, there are atoms and there are protons, electrons, and neutrons, and the protons are positively charged and the electrons are negatively charged, and neutrons have no charge. Electricity is the definition of current is electron flow. So I've written down here for my prompting, overfusing and the bridge analogy. So current flows through a wire. And you can think of the wire like a bridge. And the bridge is, like Tacoma Narrows Bridge as an example. It's rated to carry, let's say, 5 cars over it. And if you push 3 cars through it, no problem, the bridge can handle it. But if you try and push 7 cars over the bridge is going to collapse. And a fuse is exactly the same thing. Fuse is rated for 3 amps, 5 amps, 7 amps. And the reason is that that's the amount of copper trace or thickness of the wire that is there to carry the current. If you have wire that's only rated to 5 amps and you put a 7 amp fuse in, the wire is going to blow or get fried or heat up before the fuse is. The fuse is the cheapest part of the system. It's a 50-cent piece. Throw it away if it blows. Do not overfuse. That's the term. Again, I'm trying to get you to think of what something is in real life, like a bridge, and put it back to what you see in the machine, current rating, and fuses. And the note here, conventional current. So this is going to go a little bit into the weeds. I'm going to be very brief about it. Conventional current describes current that flows from the higher potential to the lower potential. I'll get into potential difference. You can think of it as current flowing from plus to minus. Electrons actually are the current, and they flow the other way. But for all intents and purposes, if you ever look at a diagram and someone tells you to start thinking in electron flow, don't. Think of it just in terms of potential. Current is conventional current, positive to negative. High potential to lower potential. So what is voltage? And voltage is potential for current. So if you were here, I think it was 2019, I had a talk about potential difference, voltage, AC, DC, and I covered in that what I call the building analogy. And I'll touch on that briefly. I won't go into as great a detail, but this is one of those analogies that's really good for people that it's like, oh, what do I do? What am I doing with this multimeter? Where do I put the lead? How does this work? The building analogy is this. If you have a building which has 10 floors on it, you can go from in the British system, it's 0, ground. In the American system, it's 1. I encourage you for this purpose to think of ground as 0, not entry level as 1, like it is here. The ground floor is when you walk into the building. That's what you expect it to be, the ground floor. And all the floors go up from there. It's exactly the same with potential difference. The black lead, often the ground, is your reference point. And all the voltage levels above it, the red lead, is where you place it. So for instance, if you have as an analogy, if you have 3 volt potential difference, you have 3 floors in the building. You have 5 volts, you have 5 floors. So why am I going to this trouble? Well, it's about reference. DC is a potential difference from one point to another, a reference point. And the reference point is always ground, the black lead. That's just the convention that people do. But ground doesn't have to be 0. Ground could be something else. So a good example here is I think this building is built on a slope. And depending on which entry you come into, you may enter on the 3rd floor, even though it's your ground level that you walked in off the street. You may go down 2 floors to the lower level where the tram line is, and that's the first floor. That's where you enter. So again, this is the reference point. If you say that where you enter the building is the ground floor, and it just in this case happens to be the 3rd floor of this building physically, the floors below it are negative. It's like a basement. It's like a lower, a basement parking lot is a good example there. The building, the stores are at 0, 1, 2, 3, 4, but the basement, B1, B2, B3 are the parking levels. And that's the negative. It's the same thing. It's where you put that reference, where you decide that reference is. And that's all DC is. A lot of people reference ground. It doesn't have to be ground. So how do you distinguish that from AC? Well, the AC doesn't quite fit into the building analogy because AC, the easiest way to think of it is the poles of the building are constantly turning back and forth. It's a little bit harder. But the key with measuring AC is the references are the 2 leads themselves. Wherever you put the 2 leads is where it is, and the current will flow back and forth. I really don't want to go too much into it because I could spend a lot of time. But to suffice it to say is the power, the electricity that comes into the machine is AC, that comes off your wall. There's a transformer in the machine. The AC is converted up and down level in voltage. It's then rectified to DC, and DC is what you'll spend most of your time measuring. The key thing is to know where the ground reference is and where you're measuring. If you think your measurement is bad, say for instance you get no 12 volts and you try and measure 12 volts, the best thing to do there is to go to another known good, a 20 volt reference or a 5 volt reference, and measure that. And if you get 5 volts at the 5 volt measurement and you don't get 12 volts at the 12 volt measurement, then 12 volts bad. But if you don't get 12 volts and you don't get 5 volts, then you're probably measuring incorrectly. And that's the thing to know, how to measure and how to determine when you're not doing what you're supposed to be doing correctly. Okay, another thing with electricity is magnetism. That's Faraday's law. Basically, when current flows through a wire, there's a magnetic field that's generated. That is the fundamental of your machine. All the electricity generates magnetic fields. Magnetic fields pull the plunger in. The plunger pulls whatever mechanical thing it's needed to pull in, and that's how your machine works mechanically. You can see that mechanically. You can see the plunger moving in. You can see the parts that are moving, but you can't see the electricity. Again, this is my focus. It's like, look at the electricity, try and think of it that way. And this final thing is a big reminder. Use your multimeter. A lot of people say, I looked at that fuse and it looks okay. Well, you don't have electron vision. That's your multimeter. Use it. It seems funny, but I mean, the number of times I've seen people say that fuse looks okay. You've got to measure it because you can't see it. Okay, so documentation. Yeah, you've all heard of it, RTFM. No, really, RTFM. The manuals document a lot of information. You'll read it once, you'll look at it and you'll say, 5% sank in and the rest, whatever. But here's the thing, if you read it again after gaining some more knowledge, you'll look at it and you'll say, I read that before. Didn't make any sense, and now it does. And maybe another 5% will sink in. And you'll do it again, and you'll do it again. And eventually, maybe the whole manual will sink in. But a lot of the stuff is there. I see a lot of people asking for help saying, hey, can you show me this? Can you post a picture of this? And it's all documented in the manual. If you learn how to read it and learn where it is, you won't need to be reliant on anyone else. Because, that's the whole point, right? You want to be able to fix the machine yourself. Inside the manuals, there are lots of wiring diagrams, and I'll show you an example of those in the following slides. Matrix charts, learn those. You don't need to learn, you should learn how to read them. The matrix charts will be different for every machine because that is a machine-specific thing, but the concept of the matrix is the same across all the machines. They use the same wires and the same fundamental capability, but they produce different specificity of features. Solenoid charts, same thing. Solenoids are listed down there. They're different for each machine. Solenoid 1 might be used for this thing in this machine and a completely different thing in a different machine. You can't tell what it's going to be, but I guarantee you that it's going to be driven the same way because the principle doesn't change. Printed circuit boards, the two main aspects for a printed circuit board, the bill of materials, what's on it, and the schematic, how it's put together logically, not physically. And there'll be a slide very briefly on the matrix theory of operation, and that's a topic unto itself. So this is a wiring diagram from a manual. It's a System 11 machine. You can actually see it says Whirlwind at the bottom. This tells you how the cabinet and all the boards are connected. It looks like a jumble of wires, it looks like a whole bunch of complicated information, but believe it or not, most of the questions that people ask, oh, I'm rewiring my flippers, one of the wires fell off, I don't know how to connect it, can someone post me a picture? Well, this area here, which I'm circling, is where all the flipper wiring diagrams are. And if you actually look, and I can't blow it up, but you can consult a manual later, you'll see there's a whole bunch of wire colors where the wires are connected, the flipper itself, more connections, and how they connect back to ground. If you learn how to read these, you won't need somebody to post you a picture. You'll be able to figure it out. It's there. It's the same with all the wiring over here. You can see all the different colors and all the connector numbers. It's all listed there. You can go to a machine, you can look at that information, you say, this is what it should be. And having said all that, there's one caveat. Williams manuals, and I'm sure that Bailey's and Gottlieb's manuals, have errors in them. They're not perfect. They're mostly correct. So what I would advise there is look at the manual, look at the machine, and if you understand how the circuits are supposed to work, you can often deduce the manual's wrong. The other place to do is look for corroborating evidence. A lot of the times the manual actually has this information printed in 2 or 3 different places. And if it's printed in one place different from another place, go look for a third place where you can find it to help corroborate. Don't trust trust but verify, I think, is the best way to treat the manuals. They do have errors. This is a matrix chart for the switches. The switch, very briefly, the switch matrix is 8 wires in one direction, a column, and 8 wires in another direction, a row. And they intersect, and they produce an 8 by 8 matrix, which is 64 lamps or switches. Why did the designers do this? Well, if each switch requires 2 wires, and you have 64 switches, that's 128 different wires that you have to wire from the head of the machine down through the playfield, the body of the machine, and all the way back up. With this electronic scheme, you only need 16 wires, 8 columns and 8 rows, and you can service 64 switches instead of 128. It's a lot easier. It adds a little bit of complexity in terms of how the matrix interacts, but less wiring is cheaper and better. So very briefly, how does the matrix work? Well, you know what? Let me get to that with a slide. You'll be able to read it and you'll see. Lamp matrix, same thing. 8 columns, 8 rows. Nothing fancy. Solenoid table, there's no matrix with the solenoid. Solenoids are just 1 through however many there are. And in System 11 machines, there are 22, unless it's Whirlwind. In WPC machines, there are 28, unless it's a Twilight Zone, in which case they add another 8. But for the most part, they're the same. And sometimes they're not used. And you'll see that, it says not used. In other cases, for machines with Fliptronic boards, there will be 8 additional solenoids available because there are 8 solenoids that drive the flippers, the power stroke and the hold stroke, the hold winding. Sometimes games only have 2 flippers. So there's 4 solenoid drives that are sitting there unused. And what do the game designers do? Oh, look, there's 4 drives. We'll put 4 solenoids in. So they reuse it. Again, that information is contained in the manual. It's in the solenoid chart table. I can't emphasize it enough. Read the manual. This is a sample of a bill of materials and a board layout. You'll see this throughout the manual. If you ever have the board in front of you, it tells you where the physical layout is, what the physical layout is of the board, and what the part numbers are. The part numbers, the designator, and the description. These are also mostly correct. Sometimes there are differences for what's on the board and what you actually see in the manual. And I suspect that that's often due to the fact that they changed the design after they printed the manual, which is why I do not trust the manual. If you ever have a choice, trust what's in the machine, wiring and on the board, unless there's evidence that somebody has tampered with the board trying to work on it previously. Because a lot of people will put in a part that looks, well, it's about the same, 4.7K, 4.3K is no different, right? So again, if it looks like somebody's worked on it, take that into consideration. This is a schematic which is similar to a wiring diagram, but it isn't. A wiring diagram describes wires and connections in the cabinet, in and around the cabinet. The schematic here describes connections that are on the board, not in the cabinet. Often the lines that you see on a schematic are copper traces. The components that you see are soldered onto the board versus wired in circuit with connectors or anything like that. That's the distinction that I want to make between a schematic and a wiring diagram. A lot of people say, we need the schematic for the cabinet. It's not a schematic, it's a wiring diagram. This is a true board schematic. We won't go into the details, but basically it's a bunch of lines connected to different places with different components, diodes, resistors, ICs. I'll cover some more of that in the second talk if this is not too much for you. This is the switch matrix, and this is the same thing in every WPC manual. It's there. It describes exactly how the switch matrix works, and if you read it, it says there, the microprocessor is constantly storing the blah, 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 and it tells you what goes up and what goes down. But essentially, the way, I'm going to paraphrase what's there is, there are 8 row switches connected to one column. The software grounds that column, and whatever row switch is closed, the software reads that and says, I ground column 1, these rows are closed. And then ungrounds column 1 and moves to column 2 and says, I ground column 2, I see what rows are closed. And it goes on through columns 1, 2, 3, 4, 5, 6, 7, 8. When it's done with 8, it goes back to column 1. And it just keeps doing this. You can think of it like, if you're old enough, an old cathode ray tube where it has to constantly sweep the electron beam down and it just keeps doing the same thing. It's exactly the same here. If the cathode ray doesn't keep refreshing, the image dies. Same thing here. It keeps refreshing and it keeps reading the state of the switches. It's exactly the same with the lamps. It says, I decide to ground whichever lamp row, and then I enable the column. It's exactly the same. One's output, one's input. It's described here. The other reason why I wanted to put this up here is that a lot of people, when they look at problems on the playfield, they don't realize that there is additional wiring that they can't see. And that wiring is contained here in the dashed box. It's on the board, but it's still wiring. You just can't see it. And I'll come to this later, but basically this dividing line here is playfield and board. And it's very important to realize that because, as you'll hear me say later, you can't find a problem on the playfield. You can't look for a problem in the playfield on the board. And you can't look for a problem on the board in the playfield. You just won't find them. And that's the reason why it's important to understand how the system is put together, where the connections are. And the next slide is the lamp matrix, and it's exactly the same thing. There is a dashed box which contains information on what's in the board, and an outside which contains information on the playfield, and the text there describes exactly the same thing. What the software does is says, I want to ground these rows, I turn this column on. Ground these rows, turn this column. It just does the same thing in a big loop. Okay, so pattern recognition. This is where the first time you open up a machine, you look inside, you go, what are all those different wires? There is order to them. If you've ever taken apart a machine, shopped it, rebuilt it, whatever else, there are three main things to think of. There is a switch harness, a lamp harness, and a what I call power or solenoid harness. And they're actually distinct, and they're all zip tied together. When you take them out of those cable clamps, you'll find that there are three distinct things that you will end up with, all zip tied together. Sometimes someone, usually not the factory, some operator will tie all the harnesses together in one big gigantic zip tie. That's not factory. The factory didn't do that. There is a pattern to how Williams did this. The lamp columns are always yellow. Sorry, let me wind back. Every wire in a Williams machine has two colors associated with it. There's the base color, and there's what's called a trace or a stripe. And the trace can be something that runs along the length of the wire or something that runs across a band of the wire. They're the same thing. Some people say, well, this wire is traced and this wire is striped. Doesn't matter. The only thing that matters is the colors. Colors will tell you what it is and how it's used. So in a Williams machine, the lamp columns are always yellow and some other trace color. The lamp rows are always red and some other trace color. Switches, columns, direct switches, solenoid groups. It's always the same. It doesn't matter what the game is. It's always the same base and stripe. Why am I saying this? Well, if you know what the color is, if you look at this wire and it's a red-green wire, you know that it's a lamp row. And then you can go consult the matrix chart to see what lamps are driven off of that row. Same thing with the switches. You see this white-red, you know straight away that's a lamp row, switch row. Solenoid drive. You see a black-blue, you know that it's one of those from solenoid 17 to 20. This is why the pattern's important. Again, there's a lot of order under the machine. It's just, unless somebody explicitly tells you what the order is, it may not be obvious. So now that we know what the base colors are, well, believe it or not, there's actually order to the trace wires too. It's not some random color that they decided to pick. There is actually an order. And if you're familiar with the resistor color codes, you'll see that order is right there. If you ever look at a resistor, there's often 3 color codes. If you have a 1% resistor, there's a 4 color code, but we won't cover that. The color tells you what the value of the resistor is. So a 472, you'll see a yellow and a violet and a red. It's a 4.7K resistor. All they did here was they used the same color order to give you an order of the trace. So lamp rows are always red. Row 1 is red-brown. Row 3 is red-orange. Row 7 is red-violet. Switch, same thing. Switch columns are green. Switch column 4 is green-yellow. Switch column 8 is green-gray. It doesn't change. You put the two together. There's a base and a stripe. Like I said, there's a lot of order there. It's just hard to see it. I hope that this allows you to see that order a lot clearer. The one caveat, and it's that bottom thing, is if the trace is the same color as the base, then it's black. So if you're looking at lamp columns, red would be a solid red wire. They don't do that. It's red-black. Violet would ordinarily be 7, so solenoid drive 7. If I go back here, you'll see solenoid group 1 is violet. So solenoid drive 7 you'd think would be violet. Well, it isn't, because that's a solid violet wire. It's violet black. That pattern, that rule holds true for everything, whites, greens, whatever. There is one exception with what Williams did later on, in terms of yellow. They used to use green-yellow for their switch columns, but unfortunately green-yellow collides with the European for ground or earth. You'll often see that in machines. Their ground and earth wire is actually a green with a yellow stripe, so they changed it to green-white. Breaks the rule a little bit. So you'll see this very commonly in WPC manuals as well, how the wires are connected. And this is just a sample, but again, you can see the pattern is there. Solenoid drives 9 to 16 are brown-based wires with stripes, and the stripes are in exactly the same order. So you look at the violet, the stripes are in exactly the same order. Looks like a jumbled mess of wires in the machine, but it's not. There's order there. Okay, so fundamentals, approaching. The way I do it is, so I ask questions. When I look at something, I ask questions based on my understanding. The thing for me is that I make no assumptions. Someone comes to me with a problem, I'll tell you quite frankly, I don't believe what you said. And the reason is that I've done this before where I've believed someone and they've provided me with information that's incorrect, and it's led me down the wrong hole. And I just wasted however much time. If I had turned around and made the assessment myself, I would come to a different conclusion. It's not a thing of malice, right? It's just that, well, I don't want to waste my time if you've made an incorrect conclusion. So when people do that and they think, what's wrong with this person? It's just I've been burned by it, so I don't do it. And I'm just trying to save you time. Don't get burned by it. The other thing that I see a lot of people do is they're not systematic enough with their approach. They'll try one thing, oh, it doesn't work. Well, I'll try this thing, oh, it doesn't work. I'll try this thing. And of course, if you don't write down what you did, you won't remember what you did and did not do, and you might do the same thing again. So always be systematic with your approach. Do the same thing every single time. Backpedal if you need to, go backwards. So this is a part of the approach. The first thing that I do when someone comes to me with a problem is I ask myself the question, is it mechanical or is it electrical? And the reason why I ask that is it's really very simple. You can't fix a mechanical problem. You can't fix a mechanical problem by looking at the electrical side of it. And you can't fix an electrical problem if it's mechanical. You're just not going to find the problem. They're just completely different things. So always ask yourself that question, is it mechanical or is it electrical? And an example of this often people say is, well, my flipper is stuck up. I press the button, the flipper stays stuck up. And how do you decide whether it's mechanical or electrical? And the easiest thing to do, people say, is turn the power off. If you turn the power off and the flipper stays up, well, it's mechanical, isn't it? Because it's not returning. The spring's broken, probably. If the flipper comes down, well, it's got to be electrical because you just cut the power. That's the reason why you should ask yourself the question, is it electrical or is it mechanical? The number of times you'll find a problem that you go down the rabbit hole. Again, it's that same thing, make no assumptions. Make your own assessment. So often, so if it's an electrical problem, this is again the further dividing. You need to ask yourself the question, is it central or is it peripheral? And this comes back to to my medical background, where it's just like, you can think of central problems as the brain and the spinal cord, and you think of peripheral problems as everything else. And it's the same thing in your machine. You think of central problems as problems in the head, the back box, and peripheral problems as problems down in the playfield, wiring to the switches. Same concept. You can't find a problem on the board. If the problem's on the board, you can't find it on the playfield. If the problem's in the playfield, you can't find it on the board. You need to make that division, much like the electrical mechanical. Keep dividing, keep breaking it down. If you're familiar with software, it's kind of like a binary search. Keep breaking the problem down in halves and halves and halves. Functionality. Okay, so understanding the system. This is a way to look at problems from a slightly different perspective. The machine has a bunch of inputs and a bunch of outputs, and they serve different purposes. You should switches. Okay, the way to think of it is switches are inputs, lamps are outputs, display is output, solenoid is output. If you're looking at a problem and someone describes the problem, try to think of it as, is this problem an input? Is this problem an output? It'll help you to decide where you want to look. The hardware, well, that's the machine. The software, that's the smarts. The thing that often people do is that they look at something and they don't think about it in terms of what the software can control and what the software cannot control. In a lot of these WPC System 11 machines, the software is the thing that's running the game program or the diagnostics, and it makes decisions, and it makes decisions based on the inputs that it gets. And based on the inputs, it decides, what am I going to do with the output? And there are some things that software can control, transistors to fire solenoids, and there's some things that software can't control, breaks in wires, blown fuses, or shorted transistors, which always lock on a solenoid. So an example of this is I turn on my machine, and this solenoid immediately locks on. That's not software. I tell you it's not software because it takes a short while for software to initialize the system and start running. If you turn on power immediately and that solenoid pulls in, software's got nothing to do with it. It's hardware. And the reason why I'm saying this is that you need to start thinking of what can cause this problem, where is it? So if it's under software control, it'll happen later on in the cycle, or you'll trigger a certain event, and then the software perhaps has a bug in it. It will start locking on solenoids or doing incorrect things. Software cannot fix broken fuses, no power. The WPC will report this to you often. It's just like, well, I can't, you turn the machine on, it'll say, check fuse F114 or F115. And that's the software reporting to you, I can't see a switch closed where I should see one. I can't fix it because there's no power. You, Mr. Operator, need to fix it. A basic understanding of the machine, conversion of energy. So a machine is really energy conversion between two states. It's primarily driven by electricity. It's electrical energy, but it uses magnets to produce mechanical energy, kinetic energy. And it actually can also be the reverse. The kinetic energy can close a switch, which produces electrical energy, which is fed back into the software. Yeah. Again, try and think of things not as just basic switches. Try and look at it at a more functional level. Okay, dividing further. Test in isolation. The number one thing that I see people do is they report problems, but they've never actually ran the diagnostic test. A lot of these machines have very, very good diagnostics, but you have to learn how to use them. Go into the software, run the switch test, get into switch test, close the switches, see what happens. The other thing a lot of people do is that they'll run a switch test and they'll close it with their finger. And of course, when they try and play it, the finger is not closing the switch, a ball is closing the switch. So always use what happens in the actual machine. Roll a ball over the switch, see what happens. That's a very easy thing to overlook. The other thing about this, about using the switch tests, is that you will see what the software sees. If you run the switch test and the switch doesn't report closed, then the software will never see it closed. No matter how many times you try and press that switch, maybe it clicks, maybe you hear it, but even if it clicks, and you test it with a multimeter and the multimeter says it closes, the wires might be broken. And if the wires are broken, it doesn't get back to the software, but the back box, and the software says, well, it doesn't report it as closed. Again, this is this divide part where you have to break it down. I cannot encourage you strongly enough to use the software tests to do your diagnosis, because what the software sees is how the software will behave when you play a game. The other thing I see a lot of people do, and this relates to the same thing, is they report things in gameplay. They will say, well, the game won't start, or when I lock a ball, the game doesn't shoot out another ball. It's just like, well, don't think of it that way. Think of, there are 3 trough switches, and the only thing the software knows is where the balls are in terms of what switches are closed in the trough. So here's an example. Before this show, my friend had a black rose. We're all really keen and eager. We turned it on, pressed that start button, no game, nothing. We loaded 3 balls, pressed that start button, nothing. And you often see people say they'll report it's just like, well, I press the start button and nothing happens. First thing to do, go into diagnostics. And what do we find? None of those trough switches register. So we put balls in there, no problem. You can physically test the switches, they're closed. But unless the software sees it as closed, it's not going to start a game. It turned out that the connector at the back had a loose wire. Put that wire in, software sees the switch, diagnostic tests work, boom, game starts. So I strongly encourage you again, do not think in terms of game features. Report the tests that you see in the report results that you see in software test. And if you do that when you ask for help, you'll more likely get a response, because then someone doesn't have to ask you, go into switch test, what do you see? Because you've already done it. And there's the example there. Failures in gameplay are almost always a result of failed input. It's that same thing, the switch is broken. The switch is either broken physically or it is disconnected out of the system. Broken wire came off, very common. Sometimes, when you're working on machines that somebody else has worked on, you will find they've wired the diode incorrectly, or they've put the wire to the wrong lead on the switch. Happens probably more often than most people would care to admit. It's the same thing again here. And it's just like, you have to know how the switches are supposed to be wired. You look at it, you say, that's wired incorrectly. And the other thing I should note, going back here, this part here tells you how to actually do the wiring. So if you look at it, you'll see the white wire goes to the anode of the diode, goes through the diode is connected to one leg of the switch itself, and the other end of the switch is the green wire. And all the switches are wired exactly the same way. But you don't need to consult this diagram. It's also up here. It's right there in the matrix chart. Same with the lamps. It's right there in the matrix chart. Like I said, it's all documented. You just have to know where to look. Oops. Okay. So incorrect switch matrix wiring, and I've seen that happen quite a lot. People said, I replaced the micro switch and now it doesn't work because they wired it incorrectly. And so finally, how do you beat it? Well, this is a lesson I learned from diagnostics, is that always try and find a single point of failure that explains absolutely everything that you see. Because it's more likely that one thing failed one time than 2 things failed one time at the same time. Always look for something that's common. How do you know? Well, I hate to say it, you need to know how the system works in order to be able to locate it. It's just how it is. Sometimes, however, there will be multiple failures, but you'll only see that single failure. And the reason why this case is true is because, well, that single failure masks everything else beyond it. You could have a shorted drive transistor that blew your fuse. Now no solenoids work. Well, the problem is you can't see beyond the blown fuse until you put the fuse in and then it blows again, and then you realize, oh, the transistor is shorted. That's what I'm talking about with multiple failures. And that's exactly what's written there. So another fundamentally important thing that I learned in my time is differential diagnosis. And what this is in the medical field is just like, well, what diseases can cause a headache? And there's a whole bunch of them. And then someone comes to you and says, I have a headache. What could it be? Well, it's the same thing here in a machine. My solenoid doesn't fire. What could it be? It could be a whole host of things. Blown fuse, broken wire, disconnected connector, failed drive transistor. Could be any of those things. But the key here is, again, if you know how it's wired, you can work through those to find where the cause is. Comes back again to the knowledge. Okay, so this is something that I know a lot of people don't like to admit, but, well, sometimes you can get defeated. You just won't find the problem. And I'm actually dealing with something in the middle right now. There's a board. I don't know what's wrong with it. The thing before you get to this point is to always look at things commonly. It's an odds game. Everything in life is an odds game. You cross the road, what are the odds you'll get run over? You get on a plane, what are the odds the plane will crash? Same thing here. What are the odds that the drive transistor shorted? What are the odds that a wire broke off? Always look for the common things. Don't look for the real rare, weird, and wonderful. The second point here, generally ignore this was the cause of my issues, so it should be the cause of yours. I see a lot of people post, I'm having this problem, and then some guy will post, well, I had something similar, it was this. Well, I had something similar, it was this. And it's just like, it does not matter what their problem was, because it's not your problem. Look at what is in front of you. Look at go back to the knowledge, work through your problem. It might have been the same problem that they encountered, but there's no reason why it should be. Your thing is your thing, and their thing is their thing. They may give you a clue, but the number of times I've seen it, it boggles my mind for me. It's just like, there's no evidence. There's absolutely no evidence that the problem that they described is the problem that you. So again, trust nothing. Not in any way malice, just trust me, you don't want to waste your time. If there's something that you can't explain, then question it. Look again, search again. Eventually you'll be able to, hopefully, figure out what it is that you did wrong, like measurements, like I described earlier. I don't get 12 volts. Well, maybe I'm not measuring it correctly because I can't figure it out. Go back, question it, measure the 5 volts, make sure you're measuring at the correct points. This one actually is interesting. Do not see what you want to see, but be guided by the findings. This one is more analogous to detectives trying to solve a murder or a crime. It's just they look and it's like, well, I think it's this person. I'm pretty sure it's this person. I'm going to try and find some evidence that it is this person. It's like, no, you don't. You can see where I'm going with this, right? It's just, you don't do that. You look at what's in front of you, you do your measurements, you examine your evidence, and you draw conclusions from what's in front of you. Don't try and force it, because if you try and force it, invariably it's going to be the wrong thing, and you're going to waste your time, and you're going to go down the wrong hole. The search is the search for of actual truth, not your truth. Again, you can be blinded by what's in front of you. Don't. If you are seeing, if what you're seeing makes no sense, then re-question your findings. And I've had to do this a lot of times. I look at it, it's just like, this doesn't make any sense to me. Go back over, do your measurements again, double check it, which leads me into make no assumptions. Because every time you make an assumption, oh, fuse looks good, fuse isn't good. Measure it, go back, do it again. Don't be afraid to admit that you're going to get defeated and asking for help. You will find problems that you can't fix. And even now, I still encounter problems I can't fix, and then it's just like, I need to ask for help. Putting it all together, switch failure. Again, this is one of those things that I was saying. The switch failure could be anywhere in this chain of how the wiring is put together. Common things commonly. It's not going to be one of these resistors. They just don't go bad unless you fry them, literally. And more often than not, it's a broken wire, an incorrectly wired diode, a wire put onto the wrong lead. Happens all the time. Everything looks good. Okay, the next common thing, active components, ICs. The 374 or the 240. Yes, that's advanced. If all of the wiring looks good, all of the placement is correct, the diode measures correctly, everything's good, you don't understand what's going on, get help. It's beyond your knowledge level. There's nothing wrong with it. ask for help, because someone else will teach you and you will learn and you will get better. Lamps, same thing. The most common cause, bulb's bad. It's just blown. And yes, you know, people say, I turned on this machine and all of the GI is bad. And guess what? Every single bulb in that GI string is blown. There's nothing wrong with the GI circuit. Yes, all those bulbs really were that bad. It happens. So common things commonly. Go for the common things. You'll more likely get it. Again, wiring, diodes, all correct, then you've got to go back to the board. And if you're uncomfortable with that, get help. Solenoid, the solenoid circuit is actually really very simple. Again, it's one of those things. On a Williams board, on a Williams system, it's really easy. There is no diode. There's just no diode. So it's on the board. I actually am running short on time, so I'm going to get to the final slide, which is this, and then I'll leave some time for Q&A. You won't know everything. If you don't know or understand something, then do some more reading. If you still cannot figure it out, then go ask for help. If you want to ask for help, it's really important that you ask for it precisely. Give as much information as possible. I often see people say, well, this rollover switch here doesn't register. It's like, no, don't describe it as under ramp or whatever. Go to the switch matrix chart, look up the switch number and say, switch 31 on this machine doesn't register. Because that's the information that someone who's looking to help you will look for. If you provide it to them, you save them the hassle of saying, which switch is it? Because you've already done it. And if you use the chart and the names, you will use something that everybody has that's common reference, not some under left departure ramp or whatever. It's just like, use the name in the manual, everyone knows what you're talking about. Always consider that who you ask for help may not trust your findings. Again, that's make no assumptions. That person's following, make no assumptions. And finally, this one, I cannot emphasize this more. Accept the help. If you don't accept it, then why did you ask for it? The number of times you see people ask for help and just reject the help that's provided, this is like, well, why did you ask for it? Accept it, try it, follow the instructions. It may not be your solution, but it's better than you were. You were stuck either way. And it's Q&A. There's a microphone over there.
Is it on? Okay. I had a quick question about like the matrix, either lamp matrix, switch matrix. Since the ground is roving, okay, it's essentially it's getting turned on. And if you measure it at any ground point, it's getting turned on and off again all the time. So if you were measuring for a good ground there, would it just no ground, or would it should be floating and you would get some kind of potential?
Well, so it's an average because it's strobed.
Yeah.
So if you have a constant, for argument's sake, 5 volt, you're going to see that 5 volt, but it's strobed. So you're going to get these peaks.
Okay.
And because your multimeter response is not fast enough, it doesn't read as frequently as required, it will give you an average of whatever it's seeing.
Okay.
Depending on how frequent the strobing is, will dictate whether it'll be 1 volt, 2 volt, 3 volt, 4 volt, 5 volt. You can't predict it. Strobing systems that strobe, often you'll need to use some kind of oscilloscope to get an accurate measurement.
So then my follow-up question would be, if you're on the oscilloscope, is there anywhere in the manual where it tells you the timing for it to get through the matrix one time, or what the frequency would be of the strobe?
If you understand how the software works, you'll have a better idea. So on these systems, a lot of the time there is a 1 millisecond timer, or approximate 1 millisecond timer. And that timer goes off every 1 millisecond. It's hardware driven, and it will send an interrupt to the processor. The processor will take that interrupt and run what's called an ISR, interrupt service routine. And the ISR is responsible for handling all the timed tasks. And matrix stuff is timed because it's strobed. So you'll find if you look at the ISR, it will constantly strobe column 1. The next ISR run will strobe column 2, column 3, column 4, all the way, and it'll just keep going in this big loop. But it's all done on a timer in the ISR.
Okay, thank you.
Any other questions? Okay, well, the Sure. You can ask, can you get the slides? I'll provide that information, and perhaps Chase can post it in some description of when he uploads the videos. The next talk will be about hardware and software. So if you have an inkling for 8-bit microprocessors and address buses and data buses, then come back. A lot of people look at schematics and it's quite mysterious. So come back and I will hopefully try and clear up some of that for you. That's at 3:30, yes.
All right. Thank you very much, Victor.